Welcome back to the session. As of now, we have gone through the different gates and their operations. Now, by using these gates, some of the simple circuits are already constructed. Now we will try to check that gates operations and their simple circuit outputs with IBM Quantum Composer. Okay, IBM Quantum Composer is a cloud platform and giving real-time access to the QPU's quantum processing units. So first, to get this one, just open Google browser and just type IBM Quantum Computing and open this link IBM Quantum Platform. And this is first we have, if you have an account, we can go for login. If you do not have an account, first register a new account, register for new account. And already I have an account, so at that time, yeah, without signing also, without login also, we can go through our Quantum Composer, but we cannot run the circuit. So that continue with IBM ID. Okay, my details are already entered, so that it is already logged in, and it is a login page of my account. So IBM Quantum Platform. Here, these are the works, the DAB works that I already completed in the previous days, and these are 13 all QPUs where quantum process units, and 13 are available actually, but at this instance 3 are available. 3 we can access, 3 quantum computers we can access. And you can see this is see with different, this is lending material tutorials, all these are available, and these are documentation and what is the procedure to go through all these things here. And this is Qiskit programming also will be available, where Qiskit is nothing but quantum information science kit, and in that, by using Python code, we can construct the quantum circuits. Now, before going into Quantum Composer, here we'll try to see the workloads is nothing but my previous works, what I've done here, and these are computer sources that I already told you, 13 quantum processor available, and these all are 13 quantum processors. And for each quantum processor that you can see here, 156 is number of qubits, is 156, 156, 156, 133, that different number of qubits processor available here. And this processor type is also Heron, Heron R2, Heron R2, Heron R2, or Eagle, like different Eagle R3, like the different, these are processor names, and different these processors are given, and it is error. And this is all about quantum computers information. And now we will try to go into our Quantum Composer, IBM Quantum Composer. Open it, and it is a composer. This composer, on the left hand side, you can see all the list of gates. All these are available gates. It is H is head mod gate, and X gate, and C0 gate, like that. All gates are available on the left hand side. And now I'll try to open a new file, and this is a new file that you can see. Now I'm going to compose a new quantum circuit. So at present, what are they see here? Q0, Q1, Q2, Q3, all these are qubits, and these are input qubits, and where C is a classical register to save the output of these quantum circuits. Okay. Now anyhow, first I'm going through the single qubit gate. That's why all these qubits are not required, so that I can remove this all these qubits, so that you simply click it and delete it. Click and delete. I want only one qubit here. This is one qubit, and similarly registers also one is required. That's why just classical register one is okay. Now it is only single qubit and single register and classical register. And you can see here, now first I'm going to check the X gate. So generally all these qubits are initialized to 0 at first. Now I'm taking, this is what X gate. So if you want to know this information, just right click on this one, info, and the NOT gate. You see, the all the information regarding this will be given here. NOT gate, also known as the Pauli exclude gate. Okay, and then this is the one. Now this is what is the main function that already we have seen, where NOT gate is nothing but when cat 0 is given, that becomes a cat 1. So that uh, this is qubit, and to know all these things, go to view and panels list. Graphical editor is already there. Code editor is to write the Python code, but we are not. I'm not familiar in the Python code, so that I just go through state vector. This is state vector I want, and probabilities, and one more here is QSphere. These three. Okay, you can see now. This is what first state vector. Which state I have taken first? It is 0 cat 0, but already this is applied. See, when it is not is applied, when not is applied, it is 0. At first it is 0 state. When X gate is applied, it becomes 1, state 1. And the probability also, without NOT gate, it is 0, probability also 0. So means the probability of cat 0 is 100%. But when NOT gate is applied, then probability of 1 is 100%, and the state is also 1. So output is 1 here, because 0 becomes 1. And this is what generally is Q sphere. Already we have seen black spheres. Black sphere is a representation for single qubit, and Q sphere is not only for single qubit, for all multiple qubits also can be shown in this Q sphere. You can see here, this is when NOT gate is there, when NOT gate is not up, when X gate is not applied, and it is 0. When X gate is applied, it becomes 1. So that it shows the state vector, and it shows the probability of that state vector of each and every qubit. And it is a black means as a Q sphere. It is a geometrical visualization of the qubits that already we have seen. Now see this output, how to measure with the quantum computers, means this is output's symbol that we can apply onto the classical register. Okay, now you can see here, first we have to save before going to run, so that here some untitled, instead of untitled you say some X. This is X gate, so save it, and after saving, then you just go setup and run. So when you go setup and run, it asks which quantum processor. So that we have 3 quantum processors, and 127, all these things it's given, but it is a very minute operation. We can do any this one. So that this, if we apply, then see it is running, program is running. Yes, program is run, it is already run, and the job results are given. So that, so new job results it is given here, that you can see here. Now this is April 9, this is the one, this is completed, that you can see, this is the one. You can see it is a histogram, that you can see the frequency means number of times. Number of times 1015 times it is done. At all the times outcome is 1. So you can see here only 9 times it is 0 0, but and 1015 times it is 1. Out of 1024 times, 1015 times output is 1, but only from 9 times it is, because this 9 times output is 0 because of the quantum error. So because of the error only we got this one, but anyhow it shows this is what the maximum probability for this one, quit 1, isn't it? This is the output of this one. Okay, it shows this one, and in this one you can see the details of this. This is when this work is done, all these things given, and it is the results. And and what is this frequency means number of times that operation was done, number of times that operate the same NOT gate operation. It is done by 10 power, means it is done 1024 times. Out of that 10,015 times output is 1, and only 9 times is output is 0, and it is because of the error that you can see. Okay, this is the one. And now when cat input 1 is cat 0 is given onto x gate, then output is 1. Now when cat 1 is given, then how to cat 1 is nothing but, then I'll try to apply one more NOT gate here. Now you see here, cat 0 of first x gate is 1, and cat 1 of the second x gate is 0, so that anyhow this cat 1 is given as input, so that becomes cat 0. So this is the one, that the same thing that you can see here. So this is a state vector, amplitude is means state vector, state is 0 and amplitude is 1, maximum amplitude that we can have, and state 0 and probability is 100% and 0 representation that you can see here. Okay, this is x. And similarly we can go with y also. Previously I already done, so that I'll show that y gate also. See, this is y gate. First see what is y gate. Y gate is, x gate is only bit flip, y gate is a bit flip and phase flip, so that when cat 0 is applied on y gate, then bit flip because 1 is there, isn't it? The state is 1 and probability is also 1, and here in pink in color that you can see. Pink in color, where pink color is nothing but the phase change that you can see here, that even in the state also pink color change, then phase angle is pi by 2. That phase angle equal to 5 by 2 because of C. Not only bit flip, phase flip was also there, that is 1. Okay, even this we can observe without this one also. We can run this one and we can show this also, the results, and run this one, so that yes, job sent to your IBM and new job results that you can see here for the Y gate. See, this is the results that you can see. Similarly, same thing, out of 1024, 1011 times output is 1 and 13 times is error that we can see. This is output of this one. Okay, and now this is when cat 0 is applied, it becomes cat 1 and phase angle is also changed by pi by 2, and now cat 1 to be applied means again not operation, so that when we prove this is x. Now you can see this is not x gate simply, so this is 1, qubit is 1, that is input, so that 1 is applied onto the y gate, then it is cat 0 that you can see 3 pi by 2, isn't it? 3 pi by 2, and is a phase angle that you can see. This is the one representation that you can see here. Phase change and bit flip both that we can observe in the case of y gate. Okay, so that, and then we can go through Hadmor gate now, because it is also one of the important gate, Hadmor gate, that we will try to see. Where what is the operation of the Hadmor gate? Hadmor gate changes from one basis state to other basis state. At first I'll try to apply 0, so that you can see here. At first I'll show, see, this is Hadmor gate. So when cat 0 is applied onto the Hadmor gate, that you can see, you can see cat is, means 0 state is 0.707, that is 1 by root 2, and 1 state is also 0.707, that is 1 by root 2, both are 1 by root 2, and these are states. And probabilities, if you take 50% of for 0 and 50% for 1, that already we know, where Hadmor plus plus is nothing but 1 by root 2 into cat 0 plus cat 1, the same thing, 50% that we can see here. And even in the representation also, cat 0, cat 1, both it is shown here, it is Hadmor gate. So same thing, we will try to apply the results of this Hadmor gate. Okay, you can see 50%, this is 52% we got, and this is 48% because of quantum error. Now I'll try to run this on the same thing. Yes, that is done, and sent, and job results. Yes, results also we got it. So now you can see this is the results of this one. You can see out of 1024 times, 499 times output is 1, and output is 0 for 525 times. It is almost a 50-50 percentage because of the quantum error. So there is some mismatch in the number, but anyhow this is the output of the head mod gate. And similarly this is when qubit 0 is applied onto head mod gate. Now to apply qubit 1 you use NOT gate here, NOT gate that we can use here. Okay, now you can see when NOT gate is applied. See, for first output we can apply later. First we'll try to see. Now you can see here previously both are in blue color. Now the color has been changed, means phase change is there. You can see here this is cat 0 and 1 by root 2, and this is cat 1, same 1 by root 2, but phase is pi here where phase is 0 here. So this color change is nothing but it is cat minus. This is cat minus, and probability is also that you can see this is 50%, this is 50%. Okay, probability is square, that's why and you can see even the representation also cat 0 and cat 1 is in pink color, so that this is phase change. So this color changes means minus, same color means plus, that you can see here, and the same thing that we can apply output here, and this is output and the state is 1. Okay, and this is probability, and this is the one when the result is applied. See, when this classical resistor is applied in the state, only one will be given, so both will not be appeared. It can store only one only. Okay, this is the one, and again this also we can run, and it is same as the cat 0. This is head mod gate. And then coming to the single qubit gates, uh, single qubit gates, if you see here once again, S gate is there. S gate is also single qubit gate, and whereas head mod gate is in between X and Z, and S gate is in between Y and Z. We'll try to see first this S gate. S gate is applied at first. Now you can see this is S gate. So when cat 0 is applied on S gate, you can see the state 0. So see what is the function operation of the S gate. So cat 0 only, there is no change here, that you can see here, the same cat 0, there is no change. And when cat 1 is applied here, when cat 1 is applied, that you can see here, so cat 1 phase angle changes, like you can see cat 1, but this adds up, yes, you can see when cat 1 is applied here, phase changes by pi by 2. The case of, see, this is pi by 2, same, this is you can see here, this is phase change, so that there is no bit blip, but there is phase flip in the case of S gate. And this also we can check with our class on our classical register, the same thing that we can see observe here. And this is what here, this is cat 0 and cat 1 for S gate that we have seen. And then these all are single qubit gates. Now I'll try to check one more C0 gate. You can see here C0 gate, where C0 gate is a, you can see first I'll try to check each and every one. See, this is a symbol for the C0 gate, and this dot is a control bit, and this plus is a target bit. At first, without applying this classical register outputs, we'll try to check. See here, this is a 1, and these two are initiated to 0, so means control is, means this is 0 0. When 0 0, output is also 0 that you can see, this is 0 0 first one, output is also 0 0. Here also you can see 0 0 is 100% and state is also 0 0 and this is 0 0 representation that you can see. Okay, now 0 0 and then next one is 0 1. See here the 0 1 order is where 1 is q0 and 0 is q1, so that this is 0 1 is nothing but this one we can 0 1, so that 0 1 we can apply here. It is 1 0, it becomes 1 0 actually. You know what this is? Yes, this is 1 0. This is same thing that we written here, 1 0, that is, you can see now. So that when control bit is 1, there is a flipping, that's why it becomes, so 1 1 is the answer that you can see, and probability is also same that you can see here. And the next one is this one here that you can see, the third case 1 0 1. Here the case is 0 1. 0 1 means when the q bit is, means control bit is 0, then there is no change in the target bit, that's why as it is 0 1 that you can see here. And at last case 1 1. So for the both the NOT gate is applied, so that you can see when the both gate not is applied, so that it is 1, so that what happens, it becomes 1 0. That same thing that is shown here, 1 0 that you can, and this we will try to check with classical. Yes, you can see how. Okay, now we'll try to run for 1 1 case on this one. Now the probability is for 0 1. Then it, when both are 1 1, the output is 0 1, so that job is sent and results had to come. Wait for results. Yes, new job results. Now you can see this is the one that this is C0 gate. So here output is 1 and output is 0. This is for previous one, I think so. Just a minute, we'll try to see all these. Yes, this is the output of this one. You can see. So these are all possible outcomes at see here 1 1, the frequency is 67, and this is only 4 times 1 0, and 0 1 is 940 times, and 0 0 is 13 times. So that here this is output more maximum probability 940 times, maximum probability 0 1, and that will be the answer. All these are quantum errors, and to minimize these quantum errors, again circuit composition is there. That is a somehow deep concept that we'll try to see in the next things. This is C0 gate, and then similarly we can have CY and CZ is also there, and swap gate also I'll try to show here. One swap gate is also 2 qubit gate, so where the swap operation is exchange of quantum bits. Now you can see first 2 qubits, they both are initialized to 0 0, so that when 0 0 is swapped, there is no change in that, that's why it is 0 0 only that you can see. But now what I'll try to do is this one first I'll apply here. Before this, you just try to remove this, and we'll try to check it now first. Right, see here now the q0 is 1, q1 is 0, so that if you see in this case, so this is 1 0, this one, which is where this is q1 and this is q0, isn't it? So that now you can see here, actually this is what this is, see this is q1 and this is q0, where q1 is 1, but here it is 0, and q1 is 0, it is 1, so that both are swapped here. The result is swapped 1, it is already swapped, both qubits are swapped, that you can see. This is the state, and the probability is 100 for 0 1 only, and it is a representation of this one 0 1 that you can see. and this will try to run by applying classical registers. Output, and it is running. Yes, job is done, and results, yes, job is. Now you can see this is a possibility. See what is the maximum probability here. So this is 1 0 990 times, and it is 1 1 only 9 times, and it is so maximum probability for 1 0, so that 0 1 becomes 1 0, that is 1. Okay, so 1 0, so this is 0 1, so that both are swapped. Okay, these are only simple operations, but we can construct more complex quantum circuits, and we can check the results also by using this quantum process. And at last I'll try to single qubit and multi-qubit, means 2 qubit also, C0 gate that I have shown, and Bell state. I want to check with Bell state, where this Bell state is an entangled state. Okay, at first I'll go through what is this Bell state means. Already we have seen in this one. See here, this is head mod gate and this is C0 gate. Now these both construct a Bell state, where Bell state is nothing but 1 by root 2 ket 0 0 plus ket 1 1. So 4 possible entangled states or Bell states are there. So one by one we'll try to check it. So that when for both it is applied, this operation anyhow it is already explained there, that anyhow results we'll try to check here. So here, see here, this is ket 0 0 ket 1 1, and this is ket 0 0, it is 50%, ket 1 1 also it is 50%, it is shown like that. And the same thing we will try to check. Zero zero 1 1 50% we should get it. I'll try to run on the quantum computer. It's running. Yes, job was done. Yes, new results. You can see here 11507 times, whereas 00463 times. Actually out of 1024 both must be same. So 512, but slightly it is 507 and it is 461, and this is error. Actually this is error, quantum computing error. This is the results of this one also. Okay, so only simple circuit without error these are constructed. Okay, this is all about this one. Thank you.